Jason has worked deeply on the questions of the greedy type algorithms for training neural nets, and he thinks about them in connection with other models like CART. And he's going to explore some fun aspects of it. So, Jason?
So thanks a lot. Is this mic on? Okay, I think it is, yeah. So thanks a lot, Andrew. And really it is a delight and wonderful being here to honor Andrew's ideas and his work. I should say at the beginning that this work I'm about to present is joint with Jonathan Siegel, who's an applied mathematician at Texas A&M. He actually really wanted to be here, but unfortunately he's actually at his own PhD supervisor's retirement event at this very moment. So, yeah, so yeah.
Who was his advisor, do you know?
Jin Chao Shu, I think he's an applied mathematician at Penn State, yeah. Okay, so a bit about Yale. Yale is my intellectual home, absolutely. Whenever I come here, there's just no shortage of people that I can talk to about different ideas and different things. So I came here in 2013 as a fresh Canadian. I didn't really know, I guess, too much about what the American life was, but after talking, actually I was a little bit nervous being around Andrew in the beginning, but I soon quickly realized that he was quite a kind, gentle person to be around, and he was always very patient. The thing about Andrew is if you work with him, he really has this very uncanny way of finding connections with different areas, and he sees things I think that a lot of other people would just miss, and just seeing that, being next to him, with this piece of paper, scratch paper, writing down different ideas and watching his mind work was really just an absolute delight. It was really, really just a treat. And I think there's just so many things that I learned from Andrew about, how to think, sometimes, keep things simple, sometimes, really being really complicated and overly technical isn't necessarily always the right way to go. And, to be patient and to diligent with things. I think these are the things that I learned from Andrew a lot. Yale's also very special, too, because, in fact, I actually met my wife in this very house. And so it's also not only a family environment, but it's also a little bit romantic to me as well. So I should also say that during this time, the department was very, very small. And I think there was maybe 4 or 5 tenured faculty at this time. And this is something that was just so special to me, is that every lunch, pretty much every lunchtime, we would all go to the Yale the Silliman College to get lunch there, and we would discuss everything from politics to research, and it really was actually in some sense like an extension of the education that we had in the Dana House, and that's something that I just really cherish. I mean, these memories will stick with me for the rest of my life. Okay, and now just a little bit of a more personal note. So I think Ed George talked yesterday about the Barron field and about Andrew's interest in gliding. So I actually did accompany Andrew, in fact, on one of these trips. I went with, I think it was your son, Peter, I think. And so yeah, we went up to upstate New York, drove there for, it was like maybe a couple hours maybe around there? 2-hour drive, yeah. And that was really a wild experience. So I don't know if you've ever seen, so normal gliders, they're launched with an airplane. Model gliders are launched with a human. And so, there's the model glider, and it's on this kind of metal rail, and then it's you're tethered to it with a rope, and then you have to run, right, to launch the glider. And Ed George also mentioned this other important aspect of retrieval. And so maybe about 20 feet in front of the launch, there's this golf cart waiting, so that after you launch it, you can go and retrieve it. And it's very important that you maintain eye contact with the airplane at all times, because if you miss it, it could go anywhere, I guess, and then that makes the retrieval very hard. So Andrew always told me, so after I launch it, you look at it, you keep your eyes on it. And I was thinking this whole time, I'm like, oh my God, I'm going to lose this guy's glider, and he's going to be so upset at me. So I don't think Andrew trusted me fully with this. So what he did was, the golf cart was at the end, and so I have this image in my mind, and I'm sitting in the golf cart waiting. And so I have this image in my mind of Andrew just running full speed, launching the glider, and then smoothly entering the golf cart and taking off. And then, I mean, to me, he just looked like this, Tom Cruise from Mission Impossible or something. And it was really quite an experience, and that's something that I'll always remember. And I also, during that time, got to meet Andrew's wonderful parents, and so it was really just a fond memory.
Yeah, wasn't there rain for a while, and you sat with Roger and Gail and I
Yeah,
in the
yeah,
car.
there was. Exactly, that's right.
And
yeah.
we talked about the commonality of our research interests
That's right.
from industry to academics.
That's right, yeah. So it was really, really just quite a wonderful time. Okay, so now back to the intellectual aspects, the academic aspects. So I first started working on these problems with Andrew when I guess was first encountered reading some of his papers. So the first one, it's been alluded to quite a bit throughout the conference, which was his work on approximation properties using sigmoidal neural networks. And then the second is his work on approximation and learning by greedy algorithms. And the second work is a really nice paper because it goes through different types of greedy algorithms and some of their statistical properties and how they can be used for learning. And so I'm actually going to talk about one of the algorithms that's in this paper. I should say that I haven't really worked on greedy algorithms for the past 5 years, but it was only in about the past year where I started talking to Jonathan really about these things, and so kind of revived my interest. So in the past year, I kind of started revisiting a lot of these things that I was doing with Andrew during the PhD. And so yeah, one of the algorithms in here is something that I'm going to talk about. Okay, so let's first of all talk about nonlinear dictionary approximation. So let's let H be a Hilbert space. And then D will be a subset of functions in this Hilbert space, which we'll call a dictionary. And let's assume that this dictionary is bounded. So all of the elements, let's say, have some norm which is finite, if I look at the maximum element in the dictionary. And so what we're interested in terms of this nonlinear approximation, are approximating, let's say, a target function f with finite linear combinations of functions from this dictionary. Okay, and so one little note to make is that these elements, these GJ elements from the dictionary, will in general depend on the target function f to be approximated. Okay, and so this kind of paradigm here has many applications, with signal processing, statistical learning theory, and then for the applied mathematicians, so including Jonathan, numerical PDEs, solutions to numerical PDEs. Okay. So here are just a few examples of nonlinear dictionaries that you could use. So maybe the more classical ones are things like trigonometric bases or orthonormal bases, wavelet bases. And then you could use other things, like Gabor filters. So when Andrew came into the picture in the early 90s, he was thinking about these dictionaries as being just sigmoids composed with some affine transformation of the inputs. So here we have a bounded activation function sigma, and that's just composed with a linear combination of the inputs. And so you could take this to be a dictionary, and then that's where the first paper where Andrew was doing those universal approximations for neural networks came in. You could also think about the dictionaries as being, for example, like decision trees. So for example, in gradient boosting with squared error, there you take the dictionary to consist of piecewise constant functions over hyperrectangles. And there are specific algorithms to find good decision trees. So for example, CART algorithm would be one. Okay, so what I'm really interested though is what are function classes for which I can expect to have reasonable approximations, and what will these function classes be that I can hopefully approximate functions from? So what we're going to do is we're going to look at the closure of, in some sense, the convex hull of these finite linear combinations of these dictionary elements. Okay, and so this is the closure taken in with respect to the norm on the Hilbert space. Okay, and so since this is a convex space, it's the unit ball of this norm. This is sometimes called the gauge, and so this is essentially just the smallest number r for which when I multiply this b1d by, I have a function that I get the function that belonging to it. So this is a norm that captures sort of the complexity of the function in some sense, and the associated variation space here is just the set of all functions in my Hilbert space that have this finite norm or finite gauge. Okay, and this space is actually a Banach space, so it has some nice properties. One thing to note is that if I have f as being an infinite expansion of these dictionary elements, then this norm here is bounded by the L1 norm of the coefficients in that expansion, for example. Okay, so for example, going back to the Barron norm, this might be something that involves like, the integral of the norm of the Fourier transform, modulus of the Fourier transform of the function. And we've seen that in previous talks. I think Max's talk. Okay, so what kind of approximation rates can be achieved by an n-term linear combination of dictionary elements on this space here, on this B1D? Well, we can do a kind of sampling argument. I think actually Max maybe went over this a little bit. But let's first think of our F as being some very large linear combination of these dictionary elements. And let's expand our dictionary to include plus or minus elements as well as the zero element. And by doing this, we can kind of rewrite the function f and assume without loss of generality that these coefficients here are positive and they sum to 1. Okay, and if not, you can kind of, so if you had a Cj which was, let's say, negative, you could absorb the sign into the Gj, but because the dictionary contained plus or minus signs, it belongs to the dictionary. Okay, so without loss of generality, you can rewrite any linear combination in this way. And this is obviously very nice because we can interpret these Cj's now as a discrete probability distribution. And if we define a random variable f such that it equals the jth dictionary element with probability Cj, then by construction, we can think of this random variable having mean equal to the target function f. And so, we've already seen this idea now a few times. So by sampling from this distribution, so looking at n independent copies of f and considering the empirical average, we know from statistics then that we have now an unbiased estimator of f, and its mean squared error, or its variance, will just be the variance of a single draw divided by the number of draws. And that's why we have this formula here. Okay, and so what we get, this is Pizier's result from the early 80s, that because this bound holds on average, there must exist a realization, and that realization has the form of functions that are, it's an n-term linear combination such that we have this bound. Okay, so the bound basically becomes, for an n-term expansion approximating a target function f, we can roughly think of the approximation rate as being 1 over n to the power half. And then the question becomes, okay, so for general dictionaries, is this optimal? And the question is, yeah, so you can come up with a dictionary. So in this case, it's actually just the L2 sequence space, and you can take the dictionary to be the standard basis vectors in that sequence space, and you can consider this function here, and you can very easily prove that no matter what n-term expansion you use, you're always going to have an error that's at least n to the negative 1/2, and so this shows that this approximation rate is in some sense the best that you can do for general dictionaries. Okay. For certain dictionaries, so ones that are particularly smooth, you can do a little bit better than this n to the 1/2 rate, and so there's a few references. And in fact, actually, Andrew and I have a paper that discusses how you can get better than n to the negative 1/2 if you have smoothness properties in your dictionary. And there's been also some follow-up work by Jonathan as well. Okay, so now what I want to do is I want to talk about greedy algorithms because, okay, so this is nice and great. This shows that there exists these n-term approximations that achieve these error bounds, but then the question becomes, okay, well, how can we actually find these in practice? How can we algorithmically find these? And so that's the next question that I want to focus on. And specifically, I want to start talking about a certain algorithm, a certain way of doing this. And the simplest one would be what's known as the pure greedy algorithm. And this one is particularly interesting because it's connected to other fairly well-established and still somewhat popular methods like projection pursuit, as well as matching pursuit. Okay, so here's some references. And the way that the algorithm works is, let's suppose for the moment that our dictionary is normalized, so all of the elements have norm 1. And let's consider the following iteration. So let's start off at 0, so f0 will equal 0. And then what I'll do is I'll update my fit by adding on a dictionary element that's maximally correlated with the residuals. And so the residuals here are just the target function minus the previous fit. And so what I'm going to be assuming now is that I can actually do this maximization here. And this is an assumption that is still not yet quite worked out. And there's indeed a lot of people that are working on this, I think including Andrew. That how do you actually do this maximization? Sorry?
You tried a lot.
We tried a lot too, yeah. And so this is a very challenging problem. In general, it's a non-convex optimization problem. And if you have d inputs, it's a d-dimensional non-convex optimization problem. So it's not terribly easy. Okay, but let's just imagine for the second that we can actually do this. Okay, and what's interesting about this algorithm is that this actually generates an expansion. And the way that you can kind of see this is, let's suppose that we had already fit the first k-1 elements in this expansion. Okay, and then if I wanted to add on, let's say, the next best expansion, or the next best term, what I would add on is exactly what the algorithm says I should add on. So this kind of minimizes this error with this residual here, with f minus the previous fit. Okay, so the next question are, what are the convergence rates of this algorithm? And many people have worked on this over the years in trying to figure this out. So in the context of projection pursuit, so Huber was the first to show that it at least converges to 0, so you have some kind of consistency in some sense.
Lee Jones, in the discussion of Huber's paper,
I think also, yes, that's right, yeah.
Hooper didn't show that.
Yeah, Lee did.
He showed it weekly.
Okay, he showed it weekly. Yeah, actually, you're right. You're right, weekly. I should have changed that to weekly. Yeah, you're right. I think I just wanted to keep things consistent in the norm, so yes, I should change that. So yeah, weekly. Okay, and then Devore and Tmelyakov showed in 96 that the rate you could get was n to the negative 1/6. And this is obviously not close to the optimal 1/2, which is what you want. Okay, and then Konygin and Tmelyakov showed in 99 that you could get this 11 over 62. So it was kind of getting better and better. And then finally, Silnichenko in 2004 gave this kind of very, very bizarre characterization. Not characterization, but upper bound on the rate. So what he showed was that this algorithm here, this pure greedy algorithm has an upper bound here, which is defined in terms of the solution to this kind of weird, strange, nonlinear equation. And this results in an exponent of about 0.182. Okay, so again, this is not optimal, but you could still, it is, yes. That is larger than 11 over 62. Yeah. Okay, so yeah, I mean, again, it's still not optimal, and in fact, actually, this isn't optimal. But you could still ask the question of, okay, what actually characterizes the rate of this algorithm? And again, this is of interest because it's connected to some other important algorithms. And so, we scratched our heads actually for quite a while, and we first of all, okay, we're like, okay, this is not optimal. It doesn't make any sense. It's just too bizarre to be able to characterize the rate of something like this. And we were working on this for quite some time, and then we finally found that, in fact, it is actually the optimal thing. So I'll take you through some of the other lower bounds. So just kind of very quickly, people over the years, showed these other lower bounds, and they almost matched, but there was still a little bit of a gap. Okay, so this was not quite fully worked out yet. And so in what I would call a very disgusting proof, we showed that, in fact, actually, this rate that Silnichenko gave in 2004 was actually the correct rate. So in other words, if you give me an exponent, alpha, which is arbitrarily close to that upper bound that I showed you previously, so that's this one here. So you give me an alpha, which is arbitrarily close to this exponent here, then I can always construct a dictionary and a Hilbert space and a function for which the error of the pure greedy algorithm is at least that rate. Okay, so in some sense, this shows that this Silnichenko rate cannot be improved, and this kind of very bizarre exponent here characterizes the fundamental limits, in some sense, of this algorithm. Okay, actually, it is an open question of whether you can choose alpha to be exactly that rate, but we're somewhat satisfied with this result for now. Okay. I should mention that there are other greedy algorithms. Oh, and by the way, I should mention that this is obviously suboptimal. So this is not the 1/2 rate that you would want. There are other algorithms, on the other hand, which do allow you to achieve the n to the negative 1/2 rate. So I'll mention a few here. So one is the orthogonal greedy algorithm. This has been explored in one of the papers also that I mentioned of Andrew's, as well as the relaxed greedy algorithm. And this is slightly different than the previous pure greedy algorithm, because you're giving yourself some freedom to downweight the previous iteration. So the fact that this achieves this n to the negative 1/2 rate was first showed by Lee Jones, who's here in 92. But again, here again, you see this inner product that you need to maximize here, and this is still an ongoing question of whether this can be done in an efficient manner. I should also mention that recent work of Jonathan's has actually showed that if the dictionary has small metric entropy, then you can actually get the orthogonal greedy algorithm to do slightly better than this n to the negative 1/2. And this is something I alluded to a little bit earlier, because I said that if the dictionary has some smoothness properties, you can get a little bit better than the n to the negative 1/2. And it turns out that you can actually also get there algorithmically, so with one of these greedy algorithms. So Jonathan has some nice work, which I encourage you to look at. It's a really nice argument. Okay, so the last thing I'm going to do is talk about what happens if you add a little bit of shrinkage to this algorithm. So I mentioned that this pure greedy algorithm is connected to gradient boosting. And so with gradient boosting, essentially what you're trying to do, actually, you can think about CART as an algorithm that's essentially, it's a greedy algorithm within a greedy algorithm. So boosting is the greedy algorithm, but then CART is the nested greedy algorithm, which is itself trying to find this maximal element. So you can kind of think about it in that way. And one of the things that's been known about boosting, of course, is that if you add a little bit of a shrinkage parameter, this can be empirically helpful. And indeed, actually, you do find that in the proofs. So if you're now studying this algorithm with this shrinkage parameter, you can get upper bounds on the error which are better than what you would have if you didn't have any shrinkage. And then you can ask the question of, okay, well, if I now choose the optimal shrinkage level, can I still get to the n to the negative 1/2? But it turns out that actually you can't.
I don't understand. If you have this freedom of this parameter, v or nu,
yeah.
Why isn't it better? Why are you
No,
are you
it is
fixing?
better. It is better, but the question is, can it get you all the way to n to the negative 1/2? That's the question.
Oh, because you're not relaxing.
I'm still not relaxing. Yeah, I'm not relaxing. So with boosting, for example, what you would do is you would shrink the.
Well,
the
why not introduce relaxing into boosting? I mean, that's what I've been telling.
Yeah, that's the whole point of
advocates.
this, is that you should, and people don't.
Yeah.
And so this is evidence, I think, that
I
you should be
remember
doing it.
an hour-long conversation with Rob Shapiro trying to help him understand that it would
Yes,
really help to
I-
relax.
Exactly. So I think that's the whole point of this, is that, so maybe I'll just finish up here, is that, so even if you do an optimal amount of shrinkage, so in the way that you would do, with classical boosting, for example, it still doesn't get you all the way to end of the negative 1/2. And so I think the takeaway of this is that not all greedy algorithms are the same. Okay, they have very different dynamics. Their convergence rates can be characterized by very different things. One is a half, one is characterized by the solution to some nonlinear equation. But I think what you really should be doing is you really should be always doing something more relaxed. You should be giving yourself the opportunity to downweight the previous iterations. And so hopefully what we're trying to do is working on some work now which will hopefully convince the community to start doing things where you do have the relaxed, and so at least which you're theoretically guaranteed to, if you can do these inner product optimizations, achieve the optimal rate. So that's my agenda now going forward, is to convince people of that in the Barron way. So now I do want to end with one little thing. So Ed made this mention yesterday about how this thermals is something that you would say to someone for sort of like good luck, good fortune in some sense. And so actually I knew about this because after going to the Barron field, I think I was included on some email announcements that were made by the glider community. And so they would always end their emails with this thermals. And so what I will say to Andrew, to you in your retirement, is thermals. So thank you.
I think I want to start the question by asking, can you give us a sense of what was involved in establishing that optimal rate for the pure greedy?
Yeah, it's exploiting the fact that you have, from these inner products, you have some amount of positive definiteness. And you can exploit that positive definiteness to get a little bit better than what you would with the previous techniques that were used to analyze this algorithm. So it's exploiting an additional constraint in some sense, and that constraint comes from the positive definiteness of inner products.
Great. Are there any questions or comments? And Junichi, can you come on up and get your equipment set? Any questions? Yes.
You can relax them, yeah, but the question of how the rates change is, or what the optimal rates are, is sort of open. But yeah, you don't actually have to directly optimize them. You can just come to within a constant factor of the optimum value of those inner products. But it's not known exactly how those change the rates and how you can characterize that. Yeah, Ed?
I know it's not exactly greedy anymore, but is there any role for improving these rates with some a little bit of randomization?
That's a great idea. Yeah, I'm actually exploring some of that right now. Like, what if you inject some randomization? Do you maybe get some kind of smoothing? It turns out that you actually do in certain cases. And so you can kind of borrow these ideas from even some Bayesian ideas, or random forest ideas. And yeah, injecting some randomness actually does help, in fact. So that's also a very interesting direction. Yeah, thanks for asking that.
There are variants of these algorithms for Bayesian posterior calculation. You can do a greedy Bayes. And so if we can sample from posteriors, or the pseudo-posteriors that arise, they will enjoy the favorable rates. Great. Thank you very much. Let's thank Jason again.